Alright, last chapter of the year. Bum, bum, bum. Oscillations at first seems intimidating because of all this stuff. Alright, and but it's not really that intimidating. In fact, for example, this is it. This right here, this right here, and this right here. Those are all intimidating looking equations, right? But we never actually, at least for the purposes of this class, use all of this stuff, and I'll talk about that in more detail in a sec. So really it's just sort of a bunch of new concepts that at first appear intimidating because they're pretty new, but then you realize, oh, that's not a big deal. And in fact, I've seen a lot of this before. So without further ado, let's walk through them. So first off, let me actually get a picture up here. I forgot to put a picture in. It'll make it easier to sort of talk about things. I'll be right back. I'm back. Alright, so we got basically a cosine curve here, right? And the cosine curve has a maximum position, and we call this the amplitude. The amplitude is the distance. So if our displacement, this is the displacement graph, if we go from a maximum positive value to I don't know if minimum is the right word, but a maximum negative value, I should say, probably. Our total displacement is the distance from here to here. Amplitude is half that. So the amplitude is like this distance. You call that x sub m. And period is the time it takes to return to the initial position. So if you start here and you go, then the period is the time it takes to get back to the original position. So you can see t is labeled here. It's this time. So far not too bad, right? It's just sort of terminology. Period is related to the frequency. Frequency is how often something happens. How frequently does it happen? And so the more frequently something happens, the less time it will take, right? To get, so if this were to happen more frequently, then to get back to the original position, which is here, took less time, right? So they're the inverse of each other. Frequency is measured in hertz. Hertz so good, hello baby, blah blah. And hertz is essentially like crap per second. It's really just inverse seconds. There's nothing. Crap stands for nothing. Nothing on the top. But as we just learned recently in the rotational units, we can take sort of a linear-esque quantity and make it rotational. And so omega, in this case, is angular frequency, sort of a rotational frequency. And all you really do is you take the quote-unquote linear frequency, or just regular frequency, and multiply it by 2 pi radians per revolution, in a sense. And so this becomes, this value has a unit of radians per second. So we replace the crap up here, which is nothing, with radians. And so you can see that just as period is the inverse of frequency, period is the inverse of angular frequency. The only difference being that 2 pi radians jive here. And then when we are dealing with something like a mass hanging on a spring and oscillating back and forth, then we can actually also quantify the angular frequency of that. So if you have, a block on a frictionless floor, it's actually touching the floor with a spring, and this block is going wow, 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 back and forth. The mass and the spring constant help determine the angular frequency. Right? As you can see, the higher the spring constant, the higher the frequency. So the stronger the spring, and the heavier the mass, you can probably imagine something more massive is going to be harder to move back and forth. So that's going to actually decrease the oscillation frequency. And then a simple pendulum is basically something at the end of a massless string that isn't oscillating back and forth too tremendously. Like the angle that it goes back and forth is tiny. Um, if as soon as the angle gets too big, then it becomes it doesn't follow this simple sort of layout. It becomes a little more chaotic. But if it is a simple pendulum and it is a massless string with a mass at the end and it's oscillating back and forth with a pretty small angle, then you can approximate the period of this pendulum with the following function. 2 pi times the square root of the length of the string, L, divided by the acceleration due to gravity. So as you can see, a pendulum will have a different period. If nothing else changes, the length of the string doesn't change, the mass stays the same, then on different planets with different accelerations, the period will be different. So it's kind of cool. A physical pendulum is something that is more like the torque unit, where we actually have moments of inertia. This is not a massless string; it's like a rod. We might have a disc here, right? If that's the case, then this you might not be able to see this very clearly, but this is like a lowercase script l for length of the string, and this is a uppercase I for moment of inertia of this physical pendulum, including all components like the rod, for example, or a disc. It doesn't have to be a rod, by the way. One of your problems at some point in this unit is just a disc, and it's rotating at some pivot point up above the center mass. So it's like it's just a disc going back and forth like this, right? Anyway, the period of a physical pendulum is 2 pi times the square root of the moment of inertia of the entire pendulum divided by mgh, where h is the height that the center of mass rises up. Right? So the higher up you raise it, that'll affect the pendulum. Period. I take that back. Do you ever say something, and while you're saying it, you're like, this is something's not right about this, but I think it's right. Sure. Anyway, yeah, I wish the book would use a different letter for H. When you first see this, you think, oh, gravitational potential energy, conservation of energy, yay. But there's a couple times, like for example, the parallel axis theorem, where you got like ICOM plus mh squared, where if you're doing if you're trying to find the moment of inertia of an object, and you're dealing with conservation of energy in that problem, it's easy if you label both this as h and then the mgh over here as h to use those as the same thing. I'm sure most of you have done that or thought about doing that at some point. So anyway, this should have a different letter in this book for that. I would label it as Zor. Anyway, H does not stand for the height that it's raised up, as I had said, and was like, that's probably not right. H is the distance from the pivot point to the center of mass. So if this is a rod and a disc, the center of mass is probably maybe here-ish. So H would be this distance. For here, the center of mass of the disc is pretty straightforward. It's right in the very center. If the pivot point is up a bit, then H is that little distance. So sorry to confuse you. If I wasn't trying to be consistent with the book, I would change this letter. But anyway, yep. So moving on, we got the angular frequency, excuse me, of a pendulum. As you can see, closely related to this. We got angular frequency equals 2 pi over period. So here's a period of a simple pendulum. So if you do the inverse and get rid of the 2 pi, you basically get that. So these two are linked through this equation here. So it's really nothing new. Now we get these things. This represents the position of an oscillator something oscillating back and forth with respect to time. So for example, this graph here is the graph of this. We got the amplitude, xm, that's the maximum value here, times the cosine, this is a cosine function, of the angular frequency times time plus the phase shift phi 5 thing is, all this stuff does is affect sort of the shape of this graph in terms of how stretched out it is, etc., etc., whether it's shifted down. Like if this first cosine function starts here, right, at the amplitude on the when x equals 0, but if you have a phase shift, that shifts it that way or that way. We're not going to use any of this, any of this, any of this for the purposes of this class. Not to say that they're not used ever, but we're just not going to use them. But I do want to talk about the relationship between this, and this. Velocity, as we learned way back, good old days, chapter 2, velocity is the derivative of position, right? So if you take the derivative of cosine, you get the negative sign. And then if you do the, what's that, the chain rule, maybe, I think it's called, you have to take the derivative of the inside with respect to t. So the derivative of omega t is just omega. So you pull the omega out, and then you get the velocity graph. So here's a sine graph, a negative sine graph, and we've multiplied the amplitude. Hold on a sec. I had to do a super Godzilla throat clearing. So we multiplied the amplitude by omega. So get the omega out here, and that's our velocity graph. You take the derivative of velocity, you get acceleration. Another chain rule, you get another omega, which makes it omega squared. The derivative of negative sine is negative cosine, and so we get that. And you can see our y-axis is multiplied by omega squared for our amplitude. And anyway, so if you notice the nice sort of circular relationship, look at how closely the position function and the acceleration function are. This is essentially the same thing. Whoops, man. Erase that. This right here is essentially the same thing as this. So the only difference between the acceleration and the position function is this negative omega squared. So we can replace all of this with just x function of t, and this is the pure definition of simple harmonic motion. The acceleration function is proportional to the position function times the negative square of the angular frequency. That's pretty cool. So this graph is just this graph here is just the negative of this graph, where the amplitude is shifted up by this much. And that's pretty cool. So the thing is, we don't actually use this cosine crap, this sine crap, this cosine crap. What we are usually concerned with in this class are the maximum values of these graphs. And as you know, both sine and cosine oscillate between 0 and 1. The maximum that a cosine function will ever be is 1. The minimum will be 0. So we're going to be concerned with basically the situation where this is 1, where this equals 1, and where this equals 1. And then so this disappears essentially, and you have just xm left over, the amplitude. So x max equals the amplitude. That's pretty straightforward. Velocity max is negative angular frequency times the amplitude, and acceleration max is negative angular frequency squared times the amplitude. And that's very straightforward. It'll be more clear when I do some problems how this is the case. And then kind of switching gears a little bit for bringing back the old conservation of energy. You know that when something's oscillating back and forth like a pendulum, that its speed is 0 at the maximum amplitude, right? You got something oscillating, it's got to stop and turn around up at the maximum point here, right? So the speed is 0 here. There is no kinetic energy. This is just potential energy. In this case, gravitational. If you have a spring, it's spring potential. We deal with springs more often than not in this unit, so we'll use the spring energy. So the total energy of an oscillating system is actually equal to the potential energy at the maximum displacement. Again, because the kinetic energy goes bye-bye. And so you can represent that with spring potential energy, where x is the amplitude, xm, 1/2 kx squared. Then you can set that, later on equal to, like, if you want to find the kinetic energy somewhere else, you know, at some other displacement, then that would equal like 1/2 kx, where x is something less than xm, plus 1/2 mv squared, because it's going to be moving if it's not at the amplitude. So it's going to have some kinetic energy. And finally, in real life, nothing oscillates back and forth forever without, like, sort of losing some energy and gradually, like, getting less and less and less and less, and then it's coming to a stop. So in real life, things damp. It's called damping. They lose energy to friction and other sources. So you can represent the amplitude as a function of time with this function, where xm is the maximum amplitude, and then as time goes on, it decreases little by little according to this negative exponential function. And there'll be like one or two problems where you deal with this. You just essentially figure out the amplitude later on at certain times. So these are just mass. These are just other constants, like the damping constant. So if you're trying to swing a pendulum in air, you would have a lower damping constant than if you try to swing a pendulum in water or honey. So those are the main concepts for chapter 15. I'm going to do some sample problems and make things more clear in that sense. And so, yeah, those will be coming soon. See you later.